Our project explores the influence of inverter compressor speed on cooling capacity and pressure variations, focusing on optimizing performance and energy efficiency. The immediate tasks include calibrating the instruments to ensure measurement accuracy and investigating the functionality and integration of the sensor and control system. The main apparatus used in this experiment includes pressure transducers, analog pressure meters, and an Arduino board. A key challenge we encountered was calibrating the pressure transducers. To address this issue, we utilized a set of known pressure capsules to perform the calibration, ensuring accurate and reliable measurements. Simultaneously, we calibrated the analog pressure meters to cross-check the input and output pressures of the compressor. Using both pressure transducers and analog pressure meters allowed us to verify our data thoroughly and enhance the overall accuracy of the experiment. The pressure transducers provided digital data, which was converted into readable information using a microcontroller. This microcontroller, integrated with the Arduino board, enabled real-time processing and monitoring of pressure data on a computer. This setup ensured that the measurements were precise and consistent, providing a robust framework for our investigation. By using a combination of these instruments and techniques, we ensured that the experimental data would be both accurate and reliable, addressing one of the critical requirements of our study. The integration of sensors and instruments was the most complex stage of the experiment, comprising three main components: setting up the pressure transducer system, interfacing with the Arduino board, and configuring the analog pressure meter setup. The pressure transducers, which operate at 24 volts, required a compatible power source. We used an adapter capable of converting 12-24 volts, which was already configured with the transducer's supply wires. The transducer's signal output, which provided a current-based signal, was connected to the Arduino using jumper wires. However, since the Arduino works with voltage signals, we had to convert the current signal to a voltage signal using resistors. To minimize noise in the signal, we incorporated capacitors, and the entire setup was built on a breadboard. For the analog pressure meters, we directly connected them to the compressor's inlet and outlet. To enable this, we modified the compressor by cutting its inlet and outlet points and installing T-bars. 4 T-bars were used to connect both the pressure transducers and analog pressure meters at these points, allowing us to measure the pressure at both the inlet and outlet accurately. The Arduino interface required a custom code, which we developed and tested to ensure compatibility and functionality. Another crucial task was measuring the compressor speed. For this, we used 2 needle probes connected to a frequency meter. These needles were plugged into the wires, transmitting pulses to the compressor, bypassing the signals from the refrigerator's controller. This method allowed us to monitor the compressor's operational speed accurately. Through careful setup and testing, we successfully integrated all components to ensure reliable data collection and analysis. After successfully assembling the experimental setup, we began collecting data from the pressure transducers, analog pressure meters, and the compressor speed monitoring system. This allowed us to observe how the inlet and outlet pressures of the compressor changed with variations in compressor speed. In a conventional, non-inverter refrigerator, the compressor operates in an on-off manner. When the internal temperature of the refrigerator reaches the desired set point, the compressor shuts down. If there is any disturbance, such as an increase in temperature, the compressor switches back on and operates at high speed until the cabinet temperature is restored to the set level. In contrast, an inverter compressor behaves differently. Instead of switching to high speed in response to a temperature disturbance, it adjusts to an intermediate level, maintaining efficiency while restoring the desired temperature gradually. On the first day of data collection, we observed the temperature variations inside the cooling cabin and monitored the compressor's operational behavior.